So you're all set. So like before, we will try to determine the different circuit parameters for this common emitter with the emitter resistance. And we'll see how the emitter resistance influence the different parameters of the amplifier. So for that, first we draw the small signal equivalent circuit. So that is the key model, and we have included the RE here, the emitter resistance. At the base, we have the source connected. Input current. At the collector, we have the load resistance connected. Okay. So we are done drawing the small signal equivalent circuit. Now it's time to do the analysis and determine the different amplifier parameters. So we start with the input resistance Ri, and write it here, the Ri. So what will be the expression for Ri?
Sir, beta plus 1
into RE plus RE.
RE plus RE, yes.
Right, exactly. So Ri, we are looking from the base side. So that is the resistance between the space point and the ground. And we have in the trace the path. In the emitter, we have small Re and capital Re. That's in the emitter side. So we apply the resistance reflection rule, and that needs to be multiplied by beta plus 1. And that we can break down it like this: beta plus 1 small Re plus beta plus 1 capital R. And what is this first part? Beta plus 1 small Re?
R pi.
Exactly. So this is R pi plus beta plus 1 capital R. What is the input resistance for common emitter amplifier? Anyone remembers?
Sir, only R pi.
Only R pi. So the input resistance for common emitter is only R pi, right? So what we can see that it increases the input resistance. When you add an emitter resistance, the input resistance increases above that of the common emitter amplifier. Common emitter amplifier input resistance is only R pi, and here increases by this amount beta plus 1 R. So we get a high input resistance. That is one feature, that common emitter with emitter resistance will have high input resistance, unlike that we have for oh my gosh, I left. We missed everything. We draw it again. It's a mistake. Okay, we start again. So let's draw the that is our T model. Small, sorry, RE. So we writing the expression for Ri, which was beta plus 1, small re plus capital R, and that we expressed as R pi plus beta plus 1 Re. And that is, we said that larger than Ri of common emitter, right? And our conclusion was that common emitter with emitter resistance has high Ri, unlike the common emitter without emitter resistance, which we say has a low Ri. Now, what is the output resistance? How much will be the output resistance? Now, in this case, if we look at the circuit here, this is the current source. An ideal current source has infinite input resistance. Now, this is like an ideal current source because it has no output resistance, right? Is output resistance, this is an open, and so it is like an ideal current source. Because we have ignored the small RE, the R naught, sorry, the R naught that we have between the emitter and the collector. So there is this small R naught, right? So that should be connected between the collector and the emitter point, but we have ignored that to simplify the analysis. So whenever we draw the T model, so we usually ignore this small R naught, right? So the circuit like this, when you ignore this small R naught, the R naught will be, the output resistance will be infinite, but that's an ideal case. But for practical amplifier, the expression for the output resistance will be like this. R naught 1 plus Gm R pi in parallel with R. So whenever you have a resistance in the emitter and you are looking from the base, the output resistance takes this form. This same expression we have also mentioned, right, for the common base amplifier, the output resistance for the common base. In the common base, we apply the input at the emitter and we have a resistance in the emitter side. And now in the common emitter with emitter resistance, we have resistance RE in the emitter. And then we have this looking from the collector side. So when we have this configuration like this, looking from the collector side, the output resistance will be given by this expression, the small r naught times this factor, which is 1 plus Gm, parallel combination of R pi. R pi is the resistance what we have here, right, between collector, sorry, the base and emitter, and this is our RE. And so that will be our output. We are showing this without the derivation. It takes some time to derive the expressions. So it's not important, but important that there's the circuit analysis basically. So what is important that you know this expression and the implication of this one and how to apply this in different circuit design. So what we can understand from here, what conclusion we can draw, that the common emitter with emitter resistance will have a very high output resistance, right? Very high. What is the output resistance for common emitter without this emitter resistance? Anyone remembers? The output resistance common
Only
emitter. Sorry?
Sir, only R naught.
Yeah, just only small R naught. So only this is the output resistance of the common emitter without emitter resistance. Now that factor is being multiplied by this factor, right? So it will have a very high because R naught itself is high, about 50 to 100K. And when you multiply this one by this factor, Gm is high. And this depends on the value of RE. It can be also in kilo ohms. So you get a very high value for the output resistance. So this one will be still much larger than this small R naught, right? And you get a very high output resistance. So adding this resistance in the emitter increases both the input and the output resistances for the amplifier circuit. Any question, guys? Okay, now we see what is the voltage gain. We start from here. So we start from writing the expression for the output voltage V naught. What will be the expression for the output voltage? Very simple, very straightforward here. V naught is just I naught RL. And what is I naught? What we can write for I naught?
Minus alpha IE.
Exactly, it's minus alpha IE. So that is our output voltage expression V naught. Now, okay. So first what we do, we write the gain expression, how we can express the gain. The overall voltage gain V naught is given by V naught by VB, V naught by Vs, sorry. And this we can divide into two factors, two gain factors. One is V naught by VB, the other is VB by Vs. So as we have done also for in previous amplifier circuits, So the same thing we're doing here. This one. So this is our voltage VB at this point, the base point. So V0 by VB is our gain from base to collector, right? This is our base point. The voltage here is VB. So from base to collector, that is the first gain expression. The second one is VB by Vs. So that is the gain from the signal, this point to the base point. Okay, now we have determined the V0, and VB is the voltage from the base point, which is basically this point, and the ground. So we know the resistance and the current, so we can easily write the expression for VB, which is the current is IE, and the resistance is small re and capital R. Okay. Okay, so the first term, first gain factor V0 by VB. So we have a minus sign here, minus alpha I, and that divided by RL, that divided by IE, RE plus RL. So I will cancel out, and we'll be left with minus alpha RL and this. Now alpha is close to 1. We know that alpha is approximately equal to 1. So we can apply this approximation and write this minus RL divided by RE plus RE. RE plus RE. So that is the gain from base to collector. And see that it is easy to remember because RL here is the resistance in the collector, and the small RE plus RL is the, sorry, it shouldn't be RL, no? Nobody is saying anything. This is RE. Right? The VB is RE plus capital R. So that is RE, not RL. Okay. So now how to see that the gain from base to collector, so base to collector V0 by VB, and that we can express as the ratio of these two resistances. One is the RL. RL is collected in the collector. So this is the resistance in the collector side, and the other, the denominator, we have small I plus capital RE. That's the resistance that is collected in the emitter side. So for the sake of convenience, we can write this like this, minus the resistance in collector divided by resistance in emitter. And that is easy to remember. And then you can straight away write down the gain expression for the common emitter with emitter resistance. That is the resistance in collector divided by resistance. Any question, guys?
Sir, what does this negative sign signifies?
What?
The negative sign.
What about the negative sign?
Sir, what does it signify?
The gain is negative.
Okay.
For positive voltage, you get negative output. For AC signal, you get 1 degree phase shift. Common emitter has negative gain, no?
Yes, sir.
What is the gain for common emitter? V0 by VB. What is the gain expression? If it is just for common emitter without emitter resistance. Do you remember?
So minus GM are not parallel RL.
Sorry. Minus GM, then we have a small r naught in parallel with capital RL, right? Which we can usually express as minus GMRL, because the R naught, as we said, usually much larger than the RL. So that is the gain expression for the common emitter with emitter resistance. So, and what is GM? How we can express GM in terms of small RE? Do you remember?
No, sir.
Okay, GM is alpha by small RE.
Okay.
We have GM. And so here you see that the gain V naught by VB will be minus alpha RL by small RE. And then this we can simplify to minus RL by RE, because alpha is approximately equal to 1. So that is how we can express the gain for the common emitter, also as the ratio of two resistance, RL resistance in the collector, RE is the resistance in the emitter, because for common emitter this part is 0, right? Without RE. So we just have a small RE. So this, from this expression you see that you can also get the gain for the common emitter without RE. In this case, just set the RE to 0, and this RL by small RE, this part will be your gain for the common emitter, right? Without RE, the same as GM RL. Now, that this is the gain for the common emitter, and this is the gain of the common emitter with emitter resistance. So, what is the effect of adding this emitter resistance on the gain? How it is affecting the gain? Yes. How the gain is affected?
Sir, I think it is decreasing the gain.
What do you think? You're not sure.
Sir, because these terms RE makes this term more smaller.
What do you mean by more smaller? Smaller should increase or decrease?
It's a decrease.
Smaller value will decrease or increase?
So smaller value will decrease the gain.
Smaller value of what?
So smaller value of V naught by VB, this portion.
No, V naught by VB, we have this expression, no?
Yes.
And now, which part you are talking about in this expression?
Sir, I'm talking about this RE.
This RE.
No, sir, the capital RE.
So if your capital RE decreases, then gain will decrease,
Increase. No, sir.
increase.
Yes, sir.
So what's the effect of the RE then? Decreasing the gain.
Uh, yes, sir.
Right?
I think so.
Decreasing the gain. You're not
Decreasing.
you're not sure.
No, sir.
Why? Anyone else? Hmm? What is the effect of RE on the gain? High school math is nothing to do with this electronics or circuit. Just high school math. Seems everybody else went to sleep. Only one person is talking in this discussion. That's okay. So what we see that for common emitter without RE, obviously when this denominator getting smaller, the overall it will increase. So this we can say is in the opposite. So that will be less than the gain of the common emitter. So gain of the common emitter, right?
Sir, another thing is that we cannot see the lines in the right side properly, sir.
You don't see the expressions?
Sir, not properly, sir. It has
Hmm.
been,
How much you can see?
sir, I can only just see alpha by RE, written alpha by RE, minus alpha by RE. That's it.
From this line V0 by VB,
Yes,
this
sir. Yes, sir.
minus this you can see, and this part you cannot see.
No, sir. In this part, only seeing minus alpha by RE.
Oh my gosh. Why it is not showing? Supposed to show, but I can see you are supposed to see.
Sir, can you zoom out the screen a little bit?
The screen is already fully jumped. Okay, let's fix this. I think it's not problem with the screen. The screen is already zoomed. Couldn't do anything there. can't erase this. Go to previous. Okay, so what I do, I write it here in next, and that will be easier. So you simplify this one, and that we can express as minus RL and the small RE, capital RE, that is the gain for common emitter with emitter resistance. And with emitter resistance, RE will be 0. So without emitter resistance, RE will be 0. And then what we get that this part is will be less than gain for the common emitter, this P0 by VB, common emitter gain, right? So the effect of adding this emitter resistance is that it reduces the gain of the common emitter amplifier. So because common emitter amplifier has gain of RL by RE, that will be higher than this. So the higher is your RE, the higher is the RE, the lower will be the gain, right? The higher is RE, the lower will be the gain. And the higher is RE, the higher will be input resistance. Right? The higher will be the output resistance, but the lower will be the gain. So that is the effect. So you can't get both at the same time. You can't get high input resistance and high gain. So if you want to increase the gain, you have to compromise, increase the input resistance, compromise on the gain. Is that clear, guys?
Yes, sir.
So we'll go to the next slide. I think this is full. So I draw this one again, couldn't copy from the previous slide, that's the problem. Okay, so here we have determined the input resistance Ri, which was R pi plus beta plus 1, capital RE, determine the output resistance, which was R naught, and then Cm R pi in parallel with RE. And now we are trying to determine the voltage gain, AV, which is we expressed as the product of two gains, which is V0 by VB and VB by VS. And here we have already determined this gain expression V0 by VB, which is minus RL and small re plus capital RE. And now we need to determine the other gain expression, which is V0 by VS, sorry, VB by VS. So what we can write for VB by Vs? VB is the voltage right at the base point. So that is our voltage VB.
Sir, Ri by Rs plus Ri.
So exactly, we apply the voltage division rule. This whole part of this side of the circuit we can replace by the Ri, the equivalent resistance, and we apply the voltage division rule, and we can just write Ri plus R this way. So as you can see that this part, this will be obviously lower than 1. So here we get the attenuation same as that for common emitter. But here what we is different here, that Ri is much larger in this case. For common emitter it was just R pi. Now that has considerably increased by this term beta plus 1 R. So we have much higher Ri. So as a result, this expression, right, will be less than 1, but it will be much closer to 1, right? So loss will be minimized at the input side. By adding the emitter resistance, it will increase the input resistance and minimize the loss. And this part will be much closer to 1 compared to common emitter without the emitter resistance. But again, then the first part, the gain from base to emitter will be reduced, right? So overall, it gets reduced. So the overall gain expression then we can express like this minus RL, then RE plus RE, and that times RI, RI plus RI. Okay, guys, any question? So now we have determined voltage gain, and now we will try to determine the current gain, which is pretty straightforward. I naught is the current AI is the output current I naught by the input current II. I naught is alpha IE with a minus sign, so minus alpha IE, and input current. What is the input current? Guys,
Sir, IB.
yeah, input current is IB. Same as the base current. Alpha I is actually the collector current IC. So that we write as minus IC by IB. And what is IC by IB?
Sir, beta.
Right, IC by IB is beta. So that is minus beta. So that's the same as the current gain of the common emitter, which is also minus beta, and which is actually high. So it has a high current gain. So, so these are the features we have learned when you add an emitter into the resistance in the emitter circuit. We get a high input resistance, Ri increases, and we get a high output resistance. Actually, it is we can use the very in front because it will be very high. Is because when the R naught gets multiplied by this factor, we get a very high output resistance, and it reduces the gain. So we get a low voltage gain, and we have a high current gain. The current gain is not affected by the RE. Guys, any question?
No, sir.
Okay, so that's it. and our discussion on the single stage amplifiers. Now, multi-stage amplifier. In most cases, the different features requirement that we need for an amplifier cannot be satisfied by a single stage amplifier. If you are using a voltage amplifier, if you need a voltage amplifier, you need to amplify the voltage signal. So what are the features we need for the good amplifier? We need high voltage gain, obviously, right? High voltage gain. And second, we need the high input resistance. And for the output resistance, actually, we need low output resistance. So these are the features we need for a good voltage amplifier. But no single amplifier can provide this, because the common emitter gives you high voltage gain but has a low input resistance. Then also high output resistance, which is opposite to what we need here. So then we go for multi-stage amplifier. So multi-stage amplifier we can show like this, right? Let's say we start with the two-stage amplifier. So this is our input signal Vi, and that is our output signal V0. We have gain A1 for the first one, gain A2, and that is your, let's say, V0 prime, the voltage here. Then overall gain we can express as V0 by Vi, that is V0 by V0 prime times V0 prime by Vi, right? And that is the gain A1 and A2. So for multi-stage amplifier, the overall gain is the product of the gains of the individual amplifiers. It's very straightforward. Right? So now let's consider a single stage amplifier, and what are the issues here. Let's say the gain is A, the input resistance is Ri, the output resistance is R0. So now you connect a signal source at the input side, source voltage Vs, source resistance Rs, and you connect a load at the output side RL, voltage there V0. So the voltage at this point is Vi at the input of the amplifier. Now, since the input resistance are Ri, so the output side, the circuit can be represented like this. Vs, Rs, and then we have this input resistance Ri. Voltage at this point is, sorry, so that will be voltage, and this part is the voltage. So that is voltage Vi. So that's not the actual amplifier circuit, but this is the kind of equivalent circuit for the amplifier at the input side. Similarly, we can draw the equivalent circuit for the amplifier at the output side. So at the output side, the amplifier gives out a voltage that depends on the input voltage. and that voltage will be the gain times the input voltage Vi. So at the output side, we can show this by a voltage source that is dependent voltage source. Right? The output side is giving a voltage, and that depends on the input voltage AVI. So that is the voltage you get at the output side, and then you have the output resistance of the amplifier that will come in series. This is the output resistance R0 that will come in series with this source, and then you have this load connected RL, and that is the voltage V0. So that's the equivalent circuit for the amplifier at the output side, the equivalent circuit for the amplifier at the input side, right? That's how we can show. And from this, you can see how the input resistance of the amplifier or the output resistance of the amplifier will affect, right, the overall output or the gain of the amplifier. Any question, guys? No questions. So, see, overall gain is our actually this is the gain of the just amplifier, right? A is the gain of the amplifier. Overall gain the V0 by Vs, right? And that will be we can express as V0 by Vi and Vi by Vs. So first we discuss about this V0 by Vi. Sorry, Vi by Vs. So Vi by Vs we get from this circuit Vi by Vs, and this is obvious. We have discussed this before. We apply the voltage division rule, and that is Ri plus Rs. Right? So and from this it is obvious this is less than 1, always less than 1. At the input side there is no amplification, there is attenuation, and the lower is Ri, the lower will be your this part. Right? So we want Ri to be as high as possible. The higher is Ri, the closer will be this to 1. And for ideal case, when Ri is infinity, this part will be 1. Right? If Ri goes infinite, so or for very high value for Ri, this we can express that if Ri is much larger than Rs. That means Rs is negligibly small compared to Ri. Practically, we cannot get infinite Ri, but we can make Ri much larger than Rs. So if that is the case, you can ignore Rs, and Ri will cancel out, you get 1. Right? So for very high value for Ri, there will be no attenuation, no signal loss. You will get full Vs at the input of so Vi will be almost equal to Vs, right? When Ri is very high, right? So we said for ideal amplifier, Ri should be infinite, input resistance should be infinite, right? So and that's why we say the ideal op-amp has infinite input resistance. That is the feature of an ideal amplifier. It should have infinite input resistance. So the common emitter IC has a low input resistance Ri, and that affects the overall output voltage because it will cause large loss of signal into the source resistance, and Vi will be substantially smaller than the Vs. So you lose some signal at the input side. That is the downside for the common emitter amplifier. At the output side, what we have this expression, right? No, sorry, we have this equivalent circuit, and the V0 is the output, and actual output of the amplifier is this voltage, and V0 will be part of this voltage. So not full of this voltage that is generated by the amplifier is transferred to the load. Part of it will go to the load, right? So how much will be that? You see that okay. So V0 will be, we can express again, we apply the voltage division rule, and that you can V0 AVI is the source voltage here, and that times the applying the voltage division rule RL given by this. So here you see that the higher is the output resistance, the higher is your output resistance of the amplifier, the lower will be your V0, right? And we know the common emitter has a high output resistance, so you will get also lose some signal at the output side, right? So if we have low output resistance, the lower will be the output resistance, the higher will be this star, right? And most of the signal voltage in that case you get transferred to the load. In ideal situation, this will be AVI if R naught is 0, right? For zero output resistance, you get full of this voltage, right, to the load. So that's the ideal situation. Similar to the ideal op-amp, we say the ideal op-amp has zero output resistance. So that's the feature of an ideal amplifier that should have zero output resistance, right? So those are the features we look for in a voltage amplifier that should have high voltage gain, should have high input resistance, and it should have low output resistance. And none of these we get in a single amplifier. Common emitter has high voltage gain, but it has a low output resistance. It has a low input resistance and high output resistance, which are opposite. So how we can satisfy, how we can meet these features, right? We can get these features in our amplifier. So you see that which configuration has the high input resistance? Does anyone remember?
So common collector.
Exactly, common collector has the high input resistance. So if you add a common collector at the input side, right? So then you satisfy that requirement of high input resistance, right? RI will be high. So you get high input resistance, you meet these features, and you minimize the loss. And we know that common collector has voltage gain which is close to 1. So VI will be transferred to the input of the amplifier, right, without much loss. So that's the common collector here is acting like a voltage buffer to transfer the voltage from the signal to this input of the amplifier without much loss. Right? And then this part will be common emitter amplifier. The purpose of the common emitter is to amplify this signal. Right? Now, in the output side, if you need to have a low output resistance, right? Then also you need to modify the circuit. You can have another amplifier stage at the output side to have low output resistance. Now, which configuration has the low output resistance?
Again common collector.
So exactly, again, common collector has the low output resistance. Okay, I have to use this one. So again, common collector, only common collector has the low output resistance, so we can add another here, let's say common collector gain AC, another common collector stays, and we note here output. So there is our output resistance, we will give a low output resistance, and here we'll have a high input resistance. And this will give us high gain. Sometimes one single stage may not be enough to get the necessary gain. Then you can have two common emitter stages, right? Here we have one, but if you need even higher gain, then you can add another one, and you can boost the gain, overall gain that way. Because the common collector stage, they do not add any gain. They will reduce gain to some extent because the gain is less than 1 always, it will never be 1. So there will be some loss of gain in both the common collector stages, but You can boost the gain if you need more gain by adding another common emitter, 2 or 3, whatever is needed. Is that clear, guys? Any question?
No, sir.
So the issues, right, that are involved for the multi are the need for the common emitter, sorry, the multi-stage amplifiers, right? Why we need multi-stage amplifiers? Oh, we need to go to the next stage. Now, multi-stage amplifiers, we can have 2 configurations. Two configurations for multi-stage amplifier. One we call the cascade. We have introduced these terms in device 1. Cascade amplifier. The other is cascade. And you will see that both the configurations play a very important role in our the integrated circuits, design of integrated circuits. So cascade amplifier will look something like this. Let's say this one we have a common head. First, this is signal, right? Let's say first stage we have a common collector. Then the output goes to common emitter here. Emitter is grounded. And then we have the load resistance, or that is V1, V0. So this transistor 1, transistor 2. So this is our, we call it the common collector, common emitter, cascade amplifier. Right? And cascade configuration will look like this. This is our common emitter amplifier. Then we have another amplifier here. V0. Okay. Like this. So that is our Q1, that is Q2. This is our common emitter configuration. What is the configuration of this one? Q2.
It's common base.
Right, so that is common base and common emitter. Yeah, so this is called the common emitter, common base, cascade amplifier. Is there any question?
No,
No,
sir.
sir.
So this is common emitter, common collector, common emitter. If you want to add another common collector, you can easily do that. So if you want to add another common collector stays here. So what we do? And that we add another common collector. The collector is grounded and the load is taken from the emitter of common collector. So that will be our RL, V naught. This is our Q3. So then you get a low output resistance and you get a high input resistance. So that will be your common collector, common emitter, again common collector, cascade, three-stage cascade amplifier. Okay, guys, that will be all for today. We have come almost to the end of the class, and next class we'll discuss how to analyze the. We need to analyze the circuits to determine the different parameters, like what we did for the single stage amplifiers, the input output resistances, the voltage and the current gains, how to analyze this the multi-stage amplifiers to determine these different amplifier parameters. Any question, guys? Okay, so I guess there's no question. So that will be all for today then. Stay well and